This is an article by Einstein from 1905, which came after the Electrodynamics of Moving Bodies article. So this article is called "Does the inertia of a body depend upon its energy content?" and its title is therefore a question. But Einstein does answer this question. And the answer to this question is yes. According to the calculations that he did in his papers, he had no doubt that this should be indeed the case. Now, let's use a formula that he derived in his previous paper, and we also derived this formula in the previous video, where the energy of a light ray, L, and this energy, let's assume that we measure it in the system XYZT, which is what he calls capital K. This system is stationary, quote unquote stationary. Then there is a moving frame, which is characterized by the variables xi, era, zeta, tau, and this system is called lowercase k. This system will measure a different energy, L star. The formula for L star with respect to L is this one. L star is equal to L times 1 minus V over C cosine phi divided by the square root of 1 minus V squared over C squared. This angle phi here is the angle between the light ray, or the direction of propagation of the wave, so it is the direction of n, the normal to the surface of the wave, with respect to the velocity v of the moving frame. So this angle here is phi. Then c is the speed of light, as we know, and v is the velocity of the moving frame, as I said. Now we assume that there is a stationary body in the system XYZ, and we will call its energy capital E0. Whereas the same body, with respect to the moving frame, will have an energy equal to H0. Now, we assume that the body sends out in a direction that makes an angle phi with the axis of x, which is the direction along which the velocity v is located. Along this direction, which makes an angle phi with x, this body is emitting a light ray whose energy is 1/2 times L. And this is measured relatively to the system XYZ, or if you want, capital K. The body is still at rest with respect to the system capital K. We assume also that the body is emitting this light ray not just in this direction, which is the direction of n, but also in the opposite direction. So it's emitting the same quantity here with an angle of pi minus phi. Now the energy E0 after this kind of emission will be equal to E1, which will be lower than E0 because I also have emitted two light rays. One has energy 1/2 times L, and the other one will have the same energy, 1/2 times L. According to the moving system, the energy will be H0. Here we will have H1, so H0 will be equal to H1 plus, we will have 1/2 L times 1 minus V over C cosine phi divided by the square root of 1 minus V squared over C squared. But we also have this second light ray, which is emitted in this direction, so we have plus 1/2 L times 1. Here we have plus V over C cosine phi, because the cosine of pi minus phi is minus cosine phi, divided by square root of 1 minus V squared over C squared. Now if we put these two together, we simply get that this is equal to H1 plus L divided by the square root of 1 minus V squared over C squared, like this. Now, if we subtract these two equations, this one and this one, we can rewrite it like this: H0 minus E0 minus H1 minus E1, and this is equal to L times 1 over square root of 1 minus V squared over C squared minus 1. Now, the two differences of the form H minus E that you see here, they have simple physical meanings. H and E are the energy values of the same body referred to two systems of coordinates which are in motion relatively to each other. One is the body being at rest in one of the two systems, X, Y, Z, and of course this body is moving with respect to the moving system. It is clear that the difference H minus E can differ from the kinetic energy of the body only by an additive constant. So this energy is the energy with respect to the system xi, era, zeta, tau if you want, and this system is indicated with the letter k, lowercase k, and therefore when we take this difference, we have some kinetic energy k0 plus some constant minus kinetic energy in the second condition, which is after the emission of the beams of the light rays, plus the same constant c, so we can cancel c, and that's equal to L times 1 over square root of 1 minus v squared over c squared minus 1, like this. From this formula we find that the kinetic energy of the body with respect to the system lowercase k diminishes as a result of the emission of light, and the amount by which it diminishes is independent of the properties of the body. Now, if v over c is small, or v squared over c squared is small, we can rewrite this expression by expanding it in a Taylor series. So it will be 1 plus, you can find that the second term here is 1 half v squared over c squared, and then there are higher order terms. With this approximation, we can write k naught minus k1 equal to 1 half L over c squared times v squared. This is the fundamental formula here. Also, this one is important, but after this expansion using Taylor series, we can easily recognize that if a body gives off the energy L in the form of radiation, its mass is going to diminish by L over c squared. This is the point at which Einstein realizes that the mass of a body is a measure of its energy content. So the answer to the question in the title of this article is yes, mass and energy are related. L over c squared is equal to delta m. In this case, you can write it as delta m because it's a decrease in the mass due to the emission of energy. And this is exactly the formula E equals mc squared written with a different notation. But it's the same thing we're talking about here. So Einstein concludes that if the theory corresponds to the facts, radiation conveys inertia between the emitting and absorbing bodies.